Have you ever built a drone using a 2-cell lithium-ion setup? Well, if you did, chances are high that you were encountering issues. Issues like jittery motors, weird flight behavior, or the drone just falling out of the sky at one point. In this video, we're going to cover the reasons for that, and together we're going to find a solution that works on nearly every setup. My name is Nick, and this is how I fly. Now, just before we continue, the usual disclaimer, anything that is shown here is just based on my experience, what I've found out. If you decide to do any of that with your own gear, then you're very welcome to do so, but I cannot take responsibility for any issues that might come up with this in the end. This doesn't mean that this is very risky or wrong to do. It's just, I have to say this because, it's electronics. Like, lots of things can theoretically go wrong, but you need to decide for yourself what you want to do and what not. So that's off the table. Now let's continue. First of all, what's the difference between lithium-ion cells and lithium polymer cells? Well, the naming is a little confusing because actually lithium polymer cells are lithium-ion cells. It's just that the electrolytes are in a lithium-ion cell liquid, whereas they are in a gel type in lithium polymer cells. And this allows lithium polymer cells to come in all different shapes and sizes, whereas this is more difficult with a lithium-ion cell. I'm not going to go into all of the differences between the two. Maybe I'll make a separate video of that. If you're interested in that, then please let me know. But for now, in order to understand the source of our problem, there's one difference which is very important to understand. Now, this difference is related to the working voltage. A lithium polymer cell can be charged up to 4.2 volts and then safely discharged until a voltage of around 3.3 volts. Measured in flight. After the flight, it's going to balance at 3.7 volts. On the other hand, lithium-ion cells can also be charged up to 4.2 volts, although that depends a bit on which kind of cell you're using, but as we're mainly using the Sony VTC6 cells, these are chargeable to 4.2 volts, and they can be discharged down to a level of 2.5 volts safely measured in flight. So that's quite a big difference between the 2.5 volts and the 3.3 volts. And this actually also plays a big part when we're now trying to understand the source of our problem, which is what we're going to do next. And in order to do that, I've built a little test setup where we can simulate what's actually happening in flight. Alright, so this is the test setup. For one, we have here a frame where I mounted a flight controller stack with an 4-in-1 ESC. This one is from Diode. It's an F722 DJI edition stack with a connector here. And it comes with a ESC board that is rated up to 30 amps, I think. So this is just your typical normal modern ESC flight controller stack. And to it, I've connected one motor. And I have connected the Crossfire Nano receiver and, well, power cable, of course. And that's it for one. Then we have a Tango 2 remote here. And most importantly, we have a regulated power supply where we can set the voltage that it will output. So what we're going to do now is we're going to simulate what is happening in flight by powering up the drone with this and then arming the motors, or arming the flight controller. That means the motor is going to spin, and then we're going to reduce the voltage down as far as we can and see what's happening. So let's do that now.
Telemetry recovered.
So drone is connected, RC connection is there as well. I'm now going to arm the motors. Alright, I'm going to put my finger down so the noise is not too annoying. And now I'm going to reduce the voltage and we'll see what's going to be happening. I started very high at 15 volts. I know that's way above what we're going to have with a 2-cell lithium-ion setup, but I have reasons for that, which you are going to see later. So you can hear the noise getting lower. That's because the motor is spinning slower at less voltage. And now let's see how far down we can go. 7 volts. Oh, alright, did you see that? It stopped working at 6.3, 6.2 volts, more like 6.3. So that's interesting. Why is that happening? Now, in the next 30 minutes or so, I'm taking you along the journey of identifying the reason for this problem and also finding a solution that works on nearly all ESCs or flight controls. If half an hour sounds like, whoa, that's too long for you, then please feel free to use the chapter markers down in the description to jump to the solution directly. However, if you ever want to do this with your own ESC or flight controller, I highly suggest watching all of it so you understand why you're doing what you're doing, and that will make things a lot easier. Now let's follow the voltage path on one of these devices. First of all, you have the battery voltage, and then comes a 12-volt regulator. That's common, and that is the same on every flight controller and ESC board that I've seen, because you cannot go directly from battery voltage, which could be up to 25.2 volts on a fully charged 6S battery, and you cannot go down from 25 to 3.3. That would just be too much energy will be aggregated, and it's gonna get too hot. That won't work. That's why you have a 12-volt regulator in the first step. Sometime in between that and the battery you have a diode, but we'll get to that later. And then after the 12-volt regulator, all the other stuff is happening. There could be more regulators, like 9 volts or 5-volt regulators. What's definitely there is a 3.3-volt regulator, at least one, maybe even two, because 3.3 volts is what the main chipsets are going to be using on these boards. Now, the thing is with these voltage regulators that they expect a certain minimum voltage to be fed to them in order to safely provide the voltage that they're supposed to be outputting. Like a 12-volt regulator needs an input voltage of 13 point something volts in order to safely output the 12 volts. If it gets less than that, then its output voltage is also gonna get lower. And it's not gonna get lower on the same level as the input voltage, but there is a difference. And this difference is the main cause of the issues that we're seeing. And we're now gonna go back to the bench and we're gonna see how much this difference actually is, so we can better understand what the problem is and how we can solve it. So here is the ESC, and we now have to find the 12-volt regulator on this. And as this is getting very tiny, I'm gonna get some help. Ta-da! Pretty nice, huh? I got myself a microscope, and this is gonna make things a lot easier for showing you guys what's going on. Because now we can put this thing here, under here, and then... isn't that much nicer and better to see? So now we have the board here, and we need to find the voltage regulator that is regulating the input voltage to the 12 volts. And first of all, we need to understand what a voltage regulator looks like. And actually, this is what a voltage regulator looks like. The ones that are used on these boards usually have on one side 2 inputs, or not inputs, but 2 pins, and on the other side 3 pins. There also are some with 1 pin on one side and 3 on the other, and actually that's the one we're looking for, with 1 pin on one side. So how can we easily find the 12-volt regulator? Now, there is a good thing that is helping us, and that is that nowadays the flight controllers support up to 6S. And this means that the voltage regulator needs to be rather large to be able to reduce the voltage from 25 to 12 volts. So what we need to do is find the largest regulator on this board. So let's do that together. We see there's another regulator here. It's named Laura, isn't that nice? Okay, and there's another regulator here, and you see from a comparison, like regulator 1, regulator 2, regulator 3, this one is by far the largest. And also it's the one with the 1 pin on one side. That's also a good sign, because these are the ones that are used on nearly any board that is supporting a 6S input. Is there another one? No. Okay, so we have these 3 regulators, and now we need to confirm which one is 12 volt. Just to make sure, let's check the other side of the ESC as well. All right, we have the shunt here, that's what it's called. It's a resistor that is there for measuring the voltage. Not the voltage, the current. So when there is a current meter, you see what the how many amperes have been drawn out of the battery, and that's why that is for. Then we have the FETs on the side, and in the middle there are the drivers for the FETs. But I don't see another regulator here. No. All right. So back to this side. What we now need to do is we need to learn which of these is actually the 12-volt regulator. And the 12-volt regulator is the one that comes directly from or is connected after the power line. So what we need to do now is we need to get our multimeter and measure which regulator is being fed with the 12 volts. So let's do that now. This is my multimeter. This is probably the cheapest one that there is in the world, but it is working okay. I had no issues with it. So we need to set our multimeter to continuity measurement, and that is the symbol down here, the one with a speaker. And now, when I have the two sensors connected to it, and I connect them to each other, it's going to beep. And that beeping means that there is, a flow of electricity between these two. Like they are directly connected. If I would put this on any metal, it's also going to beep because metal is conductive. Now, what I need to do is I need to connect one sensor here on like the, I'm going to do it from the other side, to the voltage input. And I need to keep it here. And then I need to connect the other with our regulators here and see where I have continuity. So let's start with this one here. Let's make sure we are hitting it nicely. So there's a connection here. This is actually supported with battery voltage. That's interesting. Not on this side, so this is the input. Most likely this is then the output. Let's check LoRa. So there's no direct connection here on this side, and also not on the other side. So that's not connected to battery voltage. And now let's check here. What do we have on that side here? Also continuity, so that's also directly connected to battery voltage. And this one here, no. So this is the input and this is the output. And actually here is where the battery voltage flows in, and after it's been regulated, here is where it's flowing out again. Now, given that two of the regulators actually are connected to battery voltage, the one on the top and the one on the bottom, theoretically both of them could be the 12-volt regulator, but as I said before, the 12-volt regulator usually is the largest one. I know that it is, in this case, the bottom one. And if you can, I always suggest testing this with your multimeter if it is connected directly to the battery, because the 12-volt regulator definitely is, except there is a diode in between, and we will see this on the next board that we're going to look at. Okay, so as we want to find out what the problem is, why we are losing power on the motor when we reach 6.3 volts, what we're going to do now is we're going to check what the 12-volt regulator is outputting when we reach these 6.3 volts, because that's when something on this board is not working anymore, when the input is lower than that. So what I'm going to do now is I'm going to connect a cable here, and then measure the output of the regulator when we are turning down the voltage. And what I'm actually going to do is I'm not gonna solder it to, let's move this a bit further up. Okay, I'm not gonna solder it directly here, but what I'm gonna be doing instead, I'm gonna be soldering it to this resistor here, because this also has continuity, because I need to be able to reach this pin, and why you'll see later on. This is why I'm going to solder a cable to here, and then we're going to measure the output of the 12-volt regulator. Okay, I've now soldered a cable to this resistor here. This is basically the same as the output of the regulator, because we saw with the continuity measurement that these are connected. So what I'm going to do now is we're going to go back to the setup that we had before, and then we're going to measure what the output of the regulator is. Alright, so similar setup as before. What we do not need this time is the remote and the motor, because we know that it stops turning at 6.3. We now want to understand what's happening after the regulator, and that is why I have now connected my multimeter to this cable I just soldered onto the resistor, and I'm going to connect the negative to the negative of the battery supply. I just used some crocodile clamps here, and now we need to set the multimeter to not to continuity continuity, but to voltage measurement. And as the voltage that we want to measure is between 2 volts and 20 volts, we're going to set it to 20 volts. Now, this number here will show us what comes out of the voltage regulator, and this number shows us what is inputted like VBAT, or from the power supply here. So we are now going to connect the power supply to the ESC. It now has energy, and we see the 12-volt regulator outputs 12 volts, which is perfectly fine. It's in its happy place because it gets enough voltage to output his 12 volts reliably. And now we're going to reduce the voltage to see when this value is going to change. Oh, here it is. We saw that at 13.6, 13.7. Oh, here it's still, so 13.6, this is where things are happening. So somewhere between that. And this is actually the dropout voltage of this regulator, which is around 1.6 volts. Alright, so let's see how that will develop when we go further down. Let's go to 10 volts, because then it's easier to be calculated. So we are at 100 volts now, we get 8.4, so that again is the 1.6 volts voltage difference. It's the same as before, and now let's go to 6.3, because that's the voltage where the ESC has issues. Okay, we are at 4.7. So that's still 1.6 voltage difference. So we see that it's consistent throughout, and this is the voltage where the ESC is having problems. So what we need to do is to not allow this to happen. We are back under the microscope now, and we see that this regulator here is responsible for a voltage reduction of 1.6 volts. And it is a 12-volt regulator. And as we want to fly this with a 2-cell setup, a 2-cell lithium-ion setup even further, that means we will have less than 12 volts anyway. So we don't really need this at all. What we could do is we could just remove this regulator completely, but that is a bit difficult to do. That's difficult soldering. What we could do instead, and that also will save us to change it back when we will need it in the future, what we can do instead is just connect the input and the output of this regulator directly. Because with this type of regulator, we can do that with no issues. So what I'm going to do next to test what differences we're going to see is to do exactly that. I'm going to solder a cable between these two, and then we can measure again what's happening. So I'm going to do that now. Okay, job done. I soldered a cable between these two pins here. So that means the input and the output is now connected. The regulator should be not effective anymore. And I'm going to do the same test as we did before now, just to make sure that there really is nothing else happening. And now we should be able to measure the same voltage on this line here as in the battery input voltage that comes from the power supply in this case. Alright, so we're back here. I'm now gonna fire it up with 12 volts, and ideally we're gonna see something like 12 volts or very close to it down here, because this is again what we measure after the voltage regulator. And we see a voltage of 11.8, which is a lot closer to the 12 volts, because before we had a voltage drop of 1.6, now it is 0.2. So that's already a very big step forward. Now, where does this 0.2 voltage drop come from? Well, actually, I'm not 100% sure. Usually what these boards have, or sometimes what they have, is a diode that is supposed to prevent you from creating a short circuit. And these diodes, they are called Schottky diodes. They create a voltage drop of around 0.25 volts, so that's very close to that. But actually, I was not able to find a diode on here that I could identify clearly enough. So for this board, this has to be enough. And what we're going to do now is we're going to put the test in the mode as in the beginning. So we're going to connect the crossfire again and the motor, and then we'll see how long the motor is going to run this time. Now on to the full test with the motor running. Same setup as before. I will now connect the 12 volts.
Telemetry recovered.
Crossfire has a connection. I'm now going to spin up the motors with 12 volts. The motor, it's just one. And now I'm going to reduce the voltage again, and if you remember, last time at 6.3 volts the motor stopped working, so that's going to be the interesting thing to see, what improvement we did get here. So here we go. Ha! We're already at 6.0 volts. Let's see how much we can get it down to still work. Okay. So somewhere between 5.1 and 5.2. Let's try again. See if we can hit 5.2. Yeah. So I would say at around 5.2 it stops working, which is quite an improvement down from 6.3 volts. So that's going to give us a lot more runway. I think that's a good result. With this little adjustment of the ESC, we made our board go down to 5.2 volt instead of 6.3 volt, which is quite an improvement. Ideally, I would have liked it to get even lower than that, like to 5.0 or 4.9, but in order to do that, we need to do some more tinkering, find the diode if there is one, and then how to bypass it. But on this board, this is getting too complicated, so we're going to stick to just bypassing the regulator. And this regulator, that's like the most easy thing you can do. It's also rather large, at least compared to the other SMD parts on there, so bypassing it is doable. And I think with this trick, you can get your whole setup to fly to a level which will grant you to use up most of your lithium-ion capacity. And I personally am super happy with this result. Now, to recap, what you need to do is you need to find the 12 volt regulator. It's the one that's directly connected to the battery connector of the board, and it usually is the largest one if you have a board that goes up to 6S at least. I'm not sure about boards that go up to 4S. I could figure that it might be a little smaller then and the same size as the other regulators. But usually, like I said, it's the largest one for the common boards that we're using. And then you just need to bypass the input and the output of this regulator, and then you're good. Yeah, so let's just try this out on another board, and this time I'm going to use a all-in-one board from J Hemsu, and we're just going to do the same thing as we did on this board, on the other board, so you'll see that it's usually just the same process every time. So this setup is a little simplified because like this here is a brand new board, but I had issues when I connected my my receiver to my transmitter and connected it here, and then I booted it up with no USB connection. When I armed the motors, it was just stuttering, and I did not find out why actually. And so what we're going to do now, we'll just use the USB connection to power up the motor, because the motor test in Betaflight works perfectly, which is strange. But we can see the dropout before and after our modification, so I think that's just going to be fine. So I know it's not an ideal test environment compared to the other that was better before, but it's still enough to show what the problem is and how our solution works. All right, now I'm going down. On the other board, we know that it stopped at 6.3. Let's see how low we can get here. 6.4, 6.3, 6.2, 6.1. Okay, so somewhere between 6.1 and 6.0 it stops working. Okay, and now let's do the drill. Let's try to find the regulator and then bypass it. Time for the microscope again, and let's try to see what we can find. So this is the top side of the board. Interesting what we see here. This is actually a diode. This is what I was looking for on the other board but couldn't find because of that little line here. That is a good identification. So what do we see here? There is one little regulator here on the left side, but this one is very small. This is not going to be used for 12 volts. We have another diode here on the right side. Okay, but no regulator, not the one I'm looking for. Alright, so that's the other side of it. Again, here we have the shunt, and then we see that here there is another regulator, but again, this one is also rather small, so this is not going to be responsible for the 12 volts. We see here the drivers for the MOSFETs again, the other two here, and oh, what do we see down here? This is a large regulator, like much larger than the one that we saw up here. And actually, when we compare the number on the other board, it was 8K910. So that's also a good identifier. These boards have similar titles, and after this, we'll also go through a few pictures that I grabbed from the web from other ESCs, and then we can compare and identify the 12-volt regulator together. What's also interesting here, and that's great, there is another diode right next to it, so it's super likely that this is the diode that will be responsible for another reduction of these 0.25 volts. So ideally, we will get like a direct connection from the battery to the output of this regulator here, which is going to allow us to go even lower than before. Okay, so what I'm going to be doing now, I'm going to solder a cable between the output and the input of the regulator, and then we will test again and see how low we can go then. Just to show you real quick, this is the result from my soldering, so just a cable here from the input to the output. Alright, here we go again. Let's connect beta flight and 12 volts. Let's start the motor test. And now I'm going to reduce the voltage and let's see how low we can go. Let's move this a little closer. So last time on the other board, or on this board on 6.1, 6.0 it stopped working, so let's see. Okay, we're already lower than before. Let's see how low we can go. 5.0, that is great. 4.8, 4.7, 4.6, 4.5. So we can go down as low as 4.5, and I think this is pretty awesome. Now, 4.6 or 4.5 is already an amazing result, so there is actually no need to go any further than that. But just to demonstrate you what another thing is that you can do if, like the situation was for me on the other board, if you would still have a voltage that is a bit higher than what you would prefer to see, like 5.1 or so. Another thing that you could do is this diode here is responsible for another 0.25 voltage drop. So a diode works in a way that it is supposed to prevent a short circuit. So voltage can run through one direction, but not from the other. And the line says from which direction it is blocked. So actually the voltage goes through here, down here, and then into the input and then to the output. So what we could do is we can move this cable from the input of the regulator to the input of the diode, and this way we're bypassing the diode and the regulator in one. Just one thing that I want to show you before to make absolutely sure that this is the right diode, you need the multimeter for that. So again, we set it to continuity test. And now let's test if it beeps. It does. So one side will be put here. And the other on the diode here. It's just that these lamps are a little in the way. Okay. So it beeps, means there is a connection. So from the battery, this diode is connected. Let's test here on the other side. It should not beep, yes. And now let's go from the output of the diode. Oh, there's not much space here. Whoops. This is also beeping. So that means, yes, there is a connection between this and this pin, and from the battery to the other pin here. So we now can be sure this is the Schottky diode which is responsible for preventing a short circuit. And now we're going to move this cable from here up to the input of this diode, and then we test again. Again, just to show you real quick, output regulator, input diode. All right, let's test. All right, one last time. Connect to Betaflight, connect 12 volts, spin up the motor, and now let's see how low we can go this time. So last time we hit 4.6. Gonna go down a little quicker this time. 4.6, 4.5, 4.4. So 4.4. That gave us another 0.2, 0.25 it's usually with this kind of diode. So that is an extra option that you have in case you didn't get low enough with just removing the regulator from the voltage flow. So let's recap one more time. What you have to do is you have to find the largest regulator. You can take your multimeter to measure if the input side of the regulator here on the right side does have connection with the positive wire of the battery. And if that is the case, then it doesn't seem that there is a diode in between. If you cannot make a direct connection, then like on this one here, there usually is a diode right next to it. Then you can check if the input side of the diode here does have connection with the battery here. And if it does, then check the output of the diode with the input of the regulator, and usually there you have a connection then. But in any way, this is the regulator. You don't necessarily need to test with your multimeter, because if there is one large regulator, that is the 12-volt regulator, and that is the one that you need to bypass, like we did here. And by bypassing it, you gain another 1.6, something like that, voltage range that you now can go lower. And if you like, and you can find it easily on your board, you can also bypass the diode for another around 0.25 lower voltage. It of course depends how easy it is to solder here. Like on this board, it's super easy because it's at the corner of the board, so there's no other element right next to it or something, so it's really easy to solder here. And also like this pin here is also rather easy reachable, so that is also good. Like for example, if we look with this board, let's say this here would be the diode. It actually, I thought it could be, but then again, after some multimeter testing, I don't think it is. Anyway, but soldering here is much more difficult because the other resistor is right in the way, and it's easy to create an accidental solder bridge or something. So that's why it's more difficult here. So it depends a bit on the board. Like also here, there was this MOSFET that is close to here, so it was also a little bit more tricky, but it's still doable well. Just solder the end of the cable and then put it on top of it and touch it for a second with the soldering iron, and then it should create a solid connection. So I know it's soldering, and people usually are a bit afraid and don't want to do that, but it is rather easy and the result is great, because with this you can make any ESC work with a lower voltage, which is what we need for our lithium-ion builds. I have a few disclaimers I want to talk about. Well, the first one is if you bypass the diode, you will not have any shortage, anti-shortage protection anymore. I don't personally think that this is an issue, because how often have you repaired a damaged ESC? I never did, and I could do it theoretically, but you need the replacement parts. I mean, okay, for the diode, you can just skip it, but still no one does that, or just, I don't know, 1% of all the RC pilots are doing that. The boards are easy to get, and not too expensive, so yeah, people usually don't do that. So I don't mind removing the diode or bypassing the diode, but just so you know. The other disclaimer, and that is an important one, after you have bypassed the 12-volt regulator, you cannot connect any battery higher than 3S to this board anymore for as long as you have this bypass cable in place, because you just remove basically the 12-volt regulator. So anything higher than that will go directly to the board, and the parts like the 3.3 volt regulator can only take a certain voltage, and if it's higher than that, it's just gonna die. So make sure you're not connecting anything higher than 3S. 3S is around 12 to 14 volts. That's all still okay, but do not connect anything higher than that or your board is gonna fry. If you want to do that, just remove the cable. Now, the third disclaimer is about the fact that in this video I've been mainly talking about the ESC. How can we make the lowest voltage for the ESC reachable? But for the flight control, theoretically, this is the same. However, in my experience, the flight controller can easily take voltage down to as low as 4.2 volts or something like we saw in the first test. Even if you have the receiver connected to it, like the Crossfire Nano receiver can take as low as 3.5 volts. If you have another one, you need to check what the lowest voltage is that it can work with. But that is just something you need to be aware of. And just a little hint, if you use a CADX Vista or DJI Air unit, well, DJI Air unit, I think it requires 3S as a minimum. The CADX Vista theoretically works with 2S, but the lowest voltage it can take is 6.5 volts. So if you want to use that, don't use the onboard 9 volt back anymore, especially after if you want to use a 2S lithium ion cell, because that's just not going to work. What you need is you need to have a pull-up converter that regulates the voltage up, like the opposite of the regulators on the boards that we've seen today, but a regulator that takes the input voltage and outputs a constant like 12 volts, for example. I think that's the best because then it's also always going to be reliable and stable. So yeah, these are the things that you need to think about. What components do I want to use and what voltage do they require? Because in this video, this was just about how can I make sure that the drone is going to fly and not drop out of the air. But there are a few other things that you need to think through if you want to make this happen. All right. When I was making the video, I realized that this really is a complicated topic. And I know that this is a lot of information and a lot of you will just say, oh God, I can never do this. This is too complicated. And while I can understand that, in the end, it is rather simple because you really just have to find this one large regulator and solder a cable between the input and the output of that, like the left side and the right side. And that's it. But I know, you know, it is soldering in teeny beeny little pieces, and now I can understand if you feel like that's not the right thing for you. Maybe you can ask a friend who's like more, capable of soldering than you are. But yeah, in theory, and not only in theory, like we saw today, also in reality, we can, in my opinion, rather easily have any regulator modified so that it can take a lower voltage than what it normally can take, and that will be as low as we need it to be for a 2S lithium ion setup. And I really hope that I maybe helped a few of you to make this happen and to build your, you know, that dream build you had in your head for some time but never been able to do it. And I am personally gonna build my 7-inch 2S lithium ion build soon, and I'm gonna share all the information on this channel. So stay tuned for that. And in general, this was like my first explanatory style video, and I realized several things that I want to make different next time when I do this. So, but still, any feedback that you can give, I would be super excited about that, and also just any feedback would be much appreciated about this video. And yeah, that's it. I'm looking forward to seeing you again for my next videos. If you haven't yet done so, please subscribe to my channel and click on the thumbs up for the video. That would be much appreciated. And I'm gonna see you anytime soon. Looking forward to that. Bye bye.